My name is Dr. Cherie Stabler. I'm an associate professor in biomedical engineering and surgery here at the University of Miami. And I'm director of the tissue engineering program, also at the Diabetes Research Institute. So my background is in biomedical engineering. So what does biomedical engineering have anything to do with diabetes? Basically, when I came here, Dr. Camilla Ricordi was on a search for trying to find a tissue engineer, somebody that could help facilitate designing an organ for housing islets. And so through his search, I was fortunate enough to apply for this position and was brought in as director of the tissue engineering program. And our goal basically is to serve in developing tissue engineering platforms to house islets and facilitate, address many of the challenges associated with islet transplantation. If I was going to define my role or our objectives into two main areas, one, the focus of our program is on engineering a better site to place islets. So creating a happy home for the islets. That's our primary objective. We know this from clinical islet transplantation, which is the transplantation of islets into humans at the stage that we are now. The patients that receive this have been reported to have significantly enhanced quality of life. The need for immunosuppressive drugs prevents us from treating a larger population. So one of the challenges obviously is to make for this population in which they receive islet transplantation, this to be a cure. Right now it's not a cure. It only lasts a certain period of time. And that's because of the transplant site and also because the immunosuppressive drugs are not fully effective, so the islets are still being attacked, and also they cause islet dysfunction. So that's why we've been focused on those two things, happy home, immunosuppression. We need to make sure that when we transplant the cells, they're in the best home possible. So they are in a best environment. We're not going to take the islets and put them in the desert. We're going to put them in a house that has electricity, that has plumbing, that has all the things that we need to give them. So while we've had tremendous progress with clinical islet transplantation, so with clinical islet transplantation, you take a severely diabetic patient. It's now relegated to only severely diabetic patients that receive this treatment. So these are patients in which their blood sugar levels are uncontrollable with insulin pumps or insulin injections, really controlled monitoring of their diet. They receive an islet transplantation, they get the islets within the liver. And we see very good promise with the fact that when we transplant these cells, we can achieve a cure. It's just not a long-lasting cure. We can't keep the cells alive. And we're finding that one of the challenges is the site. So the liver is not necessarily the best place. While it's working very well, we want to find a better site. Through all of these studies, what we found is one of the most promising sites, or there's several promising sites, but one of them is the omental pouch. So the omentum is actually a tissue that hangs over your abdomen, and the omentum is actually a very interesting tissue, one that we've known has shown some regenerative properties for a long time. We found that when we take our implant and put it within the omentum, that we get very good remodeling of that microenvironment. We get a lot of deposition of kind of the native environment, good vascularization and blood vessel development, those kind of things. And so we're very excited about this site. So one of the things that we really focused on is engineering a scaffolding. And a scaffolding is just like the scaffolding of a building. You know, the framework of a building when you see it go up. We're trying to design this framework of a building to house islets, so the framework of our house. And we spent a lot of time on this, and the resulting product may not be as exciting or show all this time that went into it, but basically we created this macroporous sponge. So it's kind of like a kitchen sponge in the respect that it's very porous. We basically sprinkle the islets within this sponge, and the idea is that the sponge is going to facilitate three-dimensional distribution of the islets. And this is important. If islets are clumped together, they're going to compete with each other for nutrients. The cells in the periphery are going to get all the nutrients. The cells in the center are going to be in die. So we need to distribute them out in three-dimensional space. This recapitulates more of an organ-like environment, microenvironment as well. Furthermore, this framework helps bring in blood vessels because it gives a platform for the vessels to start growing into. Right? We created a very porous environment so that this surrounding microenvironment, the surrounding cells, will come in and re-engineer it the way, respond to the islets. Once we have this base platform, our idea is we have localized islets. We can now do all these other innovative things to it. So we have, one, a retrievable implantable device. We can monitor it, we can assess it, we can remove it if we need to. But also we can now do localized drug delivery. So as opposed to immunosuppressing the whole patient, why don't we just immunosuppress where we put the islets? This can be achieved through many different means, but one of the means that we're exploring is actually using materials to release drugs. And this is not necessarily something that's 30 years ahead. This is in the clinic right now. We're very optimistic about the fact that you can take islets, transplant them into a human, and they will regulate blood sugar levels to a level to which it seems that they don't have the disease anymore. So to us, we know the potential of cell therapy, right? That's our optimism, that's our light at the end of the tunnel and what we strive for every day.